All right, let's get started. Welcome, everybody. Welcome back from the summer break, and welcome to this first fall 2020 meeting of the New York Group Series seminar. This semester, we are still going to continue meeting in the online format. So all the meetings of the New York Group Series seminar will be online via Zoom. And if you're not receiving the emails from the New York Group Series seminar mailing list, so please send me an email and I'll sign you up. The standard meeting time of the seminar this semester will be at 4 o'clock on Thursdays, 4 p.m. Eastern time on Thursdays. There will be some deviations on occasion when the seminar will meet at different times. So please send the weekly emails and also send the seminar schedule. So there are already some talks scheduled. If you would like to give a talk or if you have a speaker in mind, please email us. And there are still some slots available. So as we did during the last semester, after the talk is finished, we'll usually try to have, after the recording is turned off, we'll try to have some kind of a slightly extended discussion for those people who wish to hang around and just chat, so you don't have to disappear right away. So before I hand the microphone to the speaker, let me also remind you that when the talk starts, I'd like to everybody please to put your microphones on mute. And when you wish to ask the speaker a question, then please unmute yourself and ask the question. So that's how it works here. With that said, I'm pleased to introduce today's speaker. It's Yuri Gurevich. He's currently, I guess his main affiliation is a professor emeritus at the University of Michigan. Yuri is an eminent computer scientist, so he worked for many years as a principal researcher at Microsoft Research. He founded the research group there called Foundations of Software Engineering. He is particularly well known for developing a notion called abstract state machines. He did quite a lot of other work in theoretical computer science, also in group theory. So he received quite a few honors and awards. So he's an ACM fellow, a Guggenheim fellow, a member of Academia Europaea. He has some honorary degrees. So today he is going to tell us something on the topic about what, if anything, can be done in linear time. So Yuri, welcome, and you have the floor.
Thank you for the invite. So what, if anything, can be done in linear time? So here is the agenda. So linear time computational complexity. So first, why linear time? Why not polynomial? So among theorists, polynomial is very popular and it seems quite convenient. In practice, polynomial may be way too much. Even linear time may be excessive. So long ago in 1980s, I had debate with Steve Cook. He was defending a thesis that everything feasible is polynomial time and polynomial time is feasible. Now you can make kind of trivial thing. You say n to the 72, how is it feasible? But Steve was very sophisticated. He spoke about nature of things. And indeed it happens that natural algorithms usually have a relatively low degree of the polynomial. And to make one point, I asked, suppose IRS, American IRS wants to find whether Steve Cook paid American taxes before he left for Canada. So there are few billions of people in their database, and it should be feasible to do at least in linear time, to go through this. But in fact, it's not feasible at all. They cannot afford to go through all the files. They will find Steve in log time using the index. So here's a simple case when linear time seems quite excessive. Steve's reaction to this was, I need to think about it. Another example is, this is from my own practice. When I was at Microsoft, I worked a little bit with Bing. And there are various problems. For example, how many unique queries were there, say, for the last 24 hours? A unique query is essentially an occurrence of a query. So if you ask the same query twice, it's two different queries. And a priori, there's no problem. Everything is written down. But first, all these hard disks are located in different parts of the world. But even if it's right here, going through this hard disk and counting queries in kind of linear time, one after another, it will take you longer than those 24 hours you speak about. So it was quite a journey for people working on such problems, and what they achieved is quite amazing. So what you can do, there are very clever algorithms. So it took a couple of decades to develop them, which will estimate the number of unique queries for the last 24 hours or for the last hour with as high probability as you wish. So the algorithms are approximate and probabilistic, but they can give you as good approximation as you want and with high probability, but not 100%, but as high as needed, and it's good enough for. And those algorithms are working in essentially in fixed time, in constant time, but they have to work all the time in order to do that. Okay, now which linear time? Contrary to polynomial time, linear time is not very robust, and much depends on the computation model. So the standard linear time in computation theory is the linear time on machines like our standard machines called RAM, random access machine. By the way, random access is quite misleading. There is no randomness, there's no probabilistic process. Randomness here means arbitrary. You can access arbitrary register. The important part that you can access memory in constant time. In constant time, you can retrieve info from a register or write something into the register. So a little later, I will give a bit more details about this. By the way, this talk presupposes almost nothing, so it should be clear. And any questions at any time, I don't mind getting questions at any time. Okay, so let's consider, for example, sorting. It seems not much can be done in linear time. For example, it is well known that sorting n items requires n log n comparisons. So there seems to be no way around this lower bound. It's a mathematical result, but maybe there is. So this lower bound is given for for the case when all you can do to compare things. So when you deal with special data, then things may be different. So let me recall what an array is. An integer array of length n. It has indices 0, 1, n minus 1. And each value, it's essentially like a function. Now, or what is in computer science called data structure. By the way, it's another misleading term. It sounds completely static, data structure. In fact, an array is not only the data, it's also an algorithm which reads from and writes into a given position in constant time. But this is very important, in constant time. So arrays, if you consider arrays of natural numbers less than a given number n, these arrays can be sorted in time, in linear time, in n. Not in n log n, but in linear time. And we take advantage that we deal with numbers rather than arbitrary items. So here is an example. It's only a very small array, but you will see the algorithm very clearly. So there are 3 steps. First, create an auxiliary array of length 7. 7 so that all the entries is less than n. So our n is 7. Create is kind of programmer's term for what really machine does. It's allocate space for such an array. And then zero it, because if you deal with normal machines, when you allocate a memory, the memory may be dirty, so you need to clean it up. So you walk through and put zeros at every place. Then you do this. You traverse A. So let's start traversing A. I have 3. Then what I do, I go to B and put 1 at position 3. Remember, we start from 0. 0, 1, 2, 3. At position 3, I put 1. I continue traversing A. I see 6. I go to B and put 1 in position 6. Recall that writing and reading is constant time. Finally, I see 0 and I write 1 here. So that's the end of step 2. I'm traversing A and setting B at A of k to 1. I go k equals 0, k equals 1, and so on. So at the end, that's what I have. The same information is now encoded in positions. And now I just traverse B and output indices as I meet them, every index which has 1 rather than 0. So I start reading B, I meet 1, I output the position of it, which is 0. Do nothing, come here, position 3, here's 1, oops. I output 3, and eventually I output 6, and this way we sorted. It's quite clever. It is a very simple case, and this algorithm is generalized so you can deal with much more sophisticated data, all kind of complicated records, all the time that they have have some integer keys, what people say. Okay, so the random access machine works as follows. If you have a length, if n is the length of your input, then you use only polynomially many registers, namely registers with addresses and big O of log n, say at most 3 log n. If you take 3 log n, it will be n cube numbers. So in fact, this is a kind of gigantic array. You can retrieve value n or write into address in constant time. And these relations, equality, less or equal, greater or equal, plus, minus, are performed in constant time. And this is the standard computer architecture. Very often people also presume that you can do multiplication and division in constant time. This is a bit of a stretch, because if you look at the circuitry of your computer, the multiplication is really, let alone division, they really require n log n. But since n is typically fixed for a computer, then it looks very, to all practical purposes, it looks like a constant time, but we don't need this additional assumption. Okay, so now I'll get you acquainted with one of the most famous linear time algorithms, and it is this. Consider a string of characters, say binary characters. Now, we are interested in suffixes. For this suffix, this index G is the key of this suffix. And there are amazing algorithms which sort the suffixes. That's how people say, sort the suffixes. As a result, you get suffix array. What they mean is each suffix is represented by its key. And what you can do in linear time, it's quite amazing. You can order the keys of the suffixes in such a way that the corresponding suffixes are in the lexicographical order. Also, if I have two suffixes and one is in lexicographical order, says C sub j, just one letter, it will be before a longer suffix. Okay. So there was a lot of work on this. So this is one of the latest work with a very, and you can do it in place. So you don't need any additional place. You have your n positions, and all you do, you work within these n positions. In place suffix sorting. So now I'll explain an algorithm which is using useful algorithm for the rest of my story. So suppose you're given a formula phi in whatever logic. So I hope you remember what push-down automata are. By the way, in these discrete math classes, they typically teach non-deterministic PDAs and prove that non-deterministic PDAs and context-free grammars correspond to each other, which is very nice result from 1960s, but not super useful, because the PDAs that actually are used, so for example, in the implementation of languages like C or C++ or Java, are deterministic PDAs. And actually there was an open problem, what grammars correspond to deterministic PDAs. It's a side remark, but let me tell, it's quite an interesting story. That problem was solved by Donald Knuth. And it was quite revolutionary. Before he solved it, compiler construction was pure art. After his solution, compiler construction became much more of a science. Okay, but it's a side story. So what I mean by parse tree, so suppose you have a conjunction, then conjunction sign is at the top, will be a root, and left conjunct will give rise to a left subtree, and right conjunct will give rise to right subtree. And in computer science, trees as a rule grow down, so the root is on the top. Sounds strange why to call it a root, but too late to change. Now, so every node in the parse tree represents a subformula of the original formula. In the sense, so I take node U. If I take U and subtree under U, it will be exactly the parse tree for this subformula. Okay, now I give a definition which is very specific. It is not something well known. It's something that Itai Neeman, my collaborator, and myself, we introduced. So consider some subformula alpha. It may be represented by node U, but there may be other nodes which also represent the same formula alpha. Inside formula phi, this alpha may appear several times. So we are interested in the node which represents the very first, the leftmost occurrence of alpha. In the parse tree, this node which represents the leftmost occurrence of alpha will be first in the depth first order of the parse tree. And this node, so suppose U represents alpha, and H of U, we call it homonymy originals. If two nodes represent the same subformula, they homonymous, like in linguistics. So they have the same meaning. So the very first representative of this alpha will be called homonymy original. So, So let me return to the algorithm. So we constructed a parse tree. Now let's take phi and look at phi as a string. And now let's sort the suffixes of phi. And we produce a suffix array. Now I will traverse the suffix array once. And in the process, we'll construct pointers from every node to its homonymy original. So that's my goal. I want to construct pointers from every node to its homonymy original. Now, how can I do it? And the suffix array allows me to do it. Let me see the idea. There are some small details which I will not go into, but notice that all nodes which represent this suffix array, this particular, say, alpha, they start with alpha. And therefore, they will form a kind of, in the suffix array, they will form a contiguous interval. And the suffix, the homonymy original will be in this contiguous interval, the one with the smallest key. So that's essentially enough information to reconstruct. All details may be not obvious, but that's the idea. And please do stop me if needed, because now I'm going to some logic. So the logic which I will speak now originated in a work I did on policy and trust management. So Itai Neyman is quite a famous set theorist in UCLA, and he was visiting me when I worked on policy and trust management. And so we worked together trying to make this policy and trust management more scientific, more from first principles. And we noticed that certain things are done very, a priori, things are very complicated in logic. Algebra is much more open, and so there are simple problems and difficult problems. In logic, almost everything is quite complicated. For example, take classical logic. If you consider the propositional classical logic, and you want to decide whether a given formula is a tautology, it's NP-hard problem. If you go to intuitionistic logic, then this problem becomes p-space complete. For classical logic, it's NP complete. There is so-called linear logic, which is much more sophisticated. Then for this linear logic, propositional fragment is even undecidable. Now, but in reality, we often make reason quite fast. So let me start from first principles. So Infon is an item of information. It's not necessarily true or false. So fake news is news nonetheless, and an item of information. So a meaningful question is whether Infon is known to an agent. Now, I want to order Infons by information, and it's common in logic that truth is on the top and false is on the bottom. And in this case, truth corresponds to completely uninformative, and false corresponds so informative that it's at the bottom. So y less or equal x will mean that y is at least as informative as x. Okay. So far, just infons. Now let's introduce conjunction. So if I have two infons, I take both of them, and that gives me the conjunction. So I know information in one infon and information in the other. So this way we get a semi-lattice. Now there's, in policy and trust management, is very important is, say, Ilya said or Yuri said something. If you allow somebody access, then that's what typically how you code all these things. But for simplicity, I will just ignore all these quotations and for the moment stick just to simple. So we have conjunction. Now implication can be viewed as solution for this two inequalities. So let's see. Suppose X is A implies B. Then what do we get? A and A implies B. It certainly implies B, and so it's at least as informative as B. And B is at least as informative. So the conjunction is at least as informative as B, and B is at least as informative as A implies B. Okay. Now, so it's clear that implication solves these inequalities. Now, in principle, we would like to have the greatest solution, but the greatest solution leads to intuitionistic, immediately gives you intuitionistic implication, and suddenly everything's become p-space complete. So we'll work with weak logic. Similarly with disjunction. So we often accustomed that conjunction and disjunction are sort of dual, but here they're not so dual, because if I have two infons together, I get conjunction. I just put them together. A disjunction would be a kind of common information. Now, these two infons can be speaking in different terms, and finding this intersection may be highly non-trivial. So in fact, if you require that you can find this intersection, that leads you to intuitionistic disjunction and also to NP hardness and complicated logics. Okay, so we just live with this simplified implication and disjunction, and the resulting logic turned out to be quite remarkable. It was more expressive than anything in the literature, in access control literature, and will be very feasible, as I'm going to show you. So here is my kind of trivial logic. So if I have conjunction, from conjunction I can, this means premise, conclusion. So from X and Y I can derive X, from X and Y I can derive Y, from X and Y I can derive the conjunction. So for conjunction we have quite adequate rules. For implication we have only these two rules. Now, the second rule is a kind of triviality. So this, a professional logician would immediately see that it's not enough power, but it's enough for many purposes. I'll just consider for expository purposes only these two connectives. So we studied this logic. It has many wonderful properties. So for example, if you take a shortest derivation of a formula phi from hypothesis H, then every formula that appears here, just because it's shortest, every alpha which appears here, it will be a subformula of a hypothesis or of phi. Okay, I hope you guys are still with me. So now let me give a kind of trivial definition. I have a bunch of hypotheses, H, and bunch of queries. And multi-derivation problem is to decide which of the given queries follow from the given hypothesis. So normal derivation problem would be have one query. And here we have a whole bunch of queries. And now we have this theorem. The multi-derivation problem for the primal logic is solvable in linear time. And so it took us a while. We actually didn't even believe this was possible. I remember we were super happy when we got n log n, but eventually we pushed it down to linear. So our approach is just, instead of, I just don't care about Q, I will derive everything which can be derived from H. And so that's what I want to demonstrate in the. So now we'll explain the algorithm in the next couple of slides. If you lose me, don't worry, because the rest will nothing will depend on this algorithm. But it's quite instructive, this algorithm. So we divide all the formulas. By all the formulas, I mean we are interested only of subformulas of hypotheses and queries. So we have hypotheses and queries, and there are subformulas. That's our world. There are no other formulas for the purpose of this algorithm. So we divide all these formulas into 3 piles. In the beginning, everything is in the one pile, which is called raw formulas. And there are 2 other piles, pending and processed. Intuitively, pending and processed will be formulas which are derived from H. Oh, sorry. All hypotheses are already in pending. The rest, all hypotheses themselves, the rest of the formulas are here. And in the beginning, nothing is processed. So the distinction between pending and processed, technical because it's needed for the algorithm. Pending formulas are derivable from H, and processed also derivable. So here is the whole algorithm. Pick the first pending formula. Now apply to it all possible inference rules. And to derive more formulas. And everything which you derive, mark it pending, if it was raw. Unless you may derive something which was already pending or processed. We don't care. Now, we will have a kind of array of subformulas, and in this array we know which one is raw, which is pending, and which is processed. Now, this is a bit complicated, how you derive, and that's the problematic states, step 2. So let's consider an easy case. Suppose I have my formula alpha, and it has this form, alpha 1 and alpha 2. So my alpha is conjunction. And the rule which I want to apply to it is this. Then that's easy. I take my alpha, apply this rule, get alpha 1, check if alpha 1 was raw, I mark it pending, done. And now, difficult case where some subtleties of linear time. All I want you to give you an illustration how to deal with linear time, because it's quite unusual. So suppose I have my formula alpha, never mind what it is. The rule I want to apply is this, where alpha plays the role of x. So there are many possible y's. I have to go through all the y's, and each time to derive alpha and y. But there's a lot of y's. So how can I go, even if for a given alpha, I can do it in maybe in linear time to go through all the y's, but I cannot do it from each alpha. It will be at least n squared. So the problem arises, how can I apply this rule so fast? And here is the trick. So we have a parse tree for H and Q. So there's one tree for all these formulas. We will traverse this parse tree just once. And we'll construct so-called use lists or use sets, but in fact lists. Okay. For every homonymy original node. So let me see on the example of oops, I see disconnect. This L needs to be R, I'm sorry. You know, it's logic, syntax and semantics. Syntax says L, but semantics is R. So conjunction R. So what I do, I come to some node, since I can compute, I have already on my parse tree already are these pointers. So when I work only with homonymy originals. When I move to the next node, I jump to its homonymy original. So I look at this U. Let me put it in different ways. So each node represents some formula, but the homonymy original of that node is a kind of a canonic representative of that formula. So now, I'm looking at this U, and it may be a left child or right child of node above it. Since I'm constructing this list conjunction R, I am looking whether I'm looking from U, I can go to its parent. And I see what is the parent, what is the, suppose parent is a conjunction. If it's not conjunction, I don't care, I walk to the next node. If it's conjunction, then I put the homonymy original of this parent into the use list of U and continue. And do the same for the other lists. Sorry, I know it's kind of technicality. So if too much to absorb, this is my last slide on this. So now I'm going back. I want to apply this rule to alpha for every y. So where I will find those y's, turns out they are now all in the use list, in the appropriate use list for alpha. So I just this again, this R. So I just go through this used list or used set, and all the y's are there and nothing else. And that's how I will walk through each y twice. First time when I construct those lists, and second time when I use it. Okay, so that's how it's solved. So some extensions, adding disjunction. In fact, disjunctions I added only from the point of view of logic, we can deal with disjunctions, but disjunctions are very common in access control. So suppose you allow it only if you have US passport or UK passport, there is a disjunction. So even though disjunction could be eliminated, but that's expensive. So we expand our logic to accommodate disjunction. That's very easy. Just introduce these rules. Again, it is a weak logic for disjunction, but sufficient for most purposes in access control. A more interesting and challenging case, I worked with this fellow. By the way, this is at the time, this fellow was a student in Columbia. His advisor wrote to me that he read our original paper with Itai Neeman and found some error. And his advisor wrote to me, is it okay if he will write you and show what he found? So the student wrote to me, indeed, he found a little error, not a big deal, but very local, but nevertheless, indeed, there was an error. He found the error, found a little patch. So I asked him if he already read all the stuff, so maybe you want to do some work, huh? He was happy to do some work. And so I worked with him and we wrote several articles together. So last that I knew, he was a graduate student at ETH Zurich, ETH Zurich. So what we did, we considered transitive logic in the following sense. Suppose A implies B, alpha implies beta, beta implies gamma, gamma implies delta, then alpha should imply delta. Okay. In original logic, it's not necessary. You may have alpha implies beta, beta implies gamma, but you may be not able to derive alpha implies gamma. It's a weak logic. So we added this transitivity, and technically it became much harder, but it worked. Then all these three guys were students at the time. So this Colombian student, this was Russian student, and Artyom Melentiev and Orel, by the way, from same university that Olga Harlampovich and I am from Ural State University. And this fellow is an Israeli student. So in, let's see, conjunction as sets, let me say a little bit about it. So in this our original logic, from X and Y, you can derive Y and X. But for example, X and Y implies with Z does not entail Y and X implies Z. Oops. And similarly, Z implies X and Y does not entail Z imply Y and X, and many other formulas like that. So the idea was to replace conjunction with a set. So if this is a set, then order doesn't matter. And so certainly these formulas will be trivially true. And this was quite hard. And the problem that sets are not constructive objects. So suppose Ilya and I decided to write a paper, and none of us should be the first one. We want, so we did equally, nobody appears first. It's impossible. Lists are constructive objects, but sets are not. So standard solution is to represent sets of sequences ordered lexicographically. So in logic, probably in group theory, the same. Certainly in logic and in computer science, it's a standard procedure. If there is a paper of Gurevich Kapovich, it doesn't mean that Gurevich did more work. It's just lexicographic ordering. But
I'm sure that there exist creative solutions. For instance, a journal can have a random order of authors that changes, every second or every other minute or something. Yes. They simply have not considered it yet.
Right. If you do it dynamically, yes, dynamically, but statically, it's very hard. Okay. But then there is a problem because you don't. That's what we did, but then you don't really deal with sets. You deal with their representation. So at the end, we were able to prove that our algorithm works in expected linear time. And which, from the point of view from the practical point of view, for the practice, it doesn't really matter. Expected linear time, well, one should be careful. For example, the standard simplex algorithm. Expected depends on what the probability distribution is. So the average behavior of, say, simplex is if you compute the kind of uniform probability distribution, then the average turns out to, very high, but in reality, it works in simplex work in n log n. So there was a complicated story how it happens. So in our case, we don't introduce any randomness on inputs. Only our algorithm introduces randomness as it works. Okay. And okay, so this is, I think that's the end of it. Okay, thank you. I'm done.
All right. Okay, all right. Thank you very much. Let's thank the speaker.
Okay.
All right. Okay, so now if there are any questions to Yuri, you're welcome to ask them. So those who wish to ask questions are welcome to unmute themselves.
Let me say something. When you see new material, which is hard to absorb, people are shy to ask naive questions. To this, I want to say there are no stupid questions, only stupid answers.
So I was trying to think, I mean, can you think of any algorithms that are more specific to group theory that are interesting and that actually work in linear time as related to, let's say, this random access machine model?
No, I didn't think about group theory, but in fact, this talk and the whole bunch of papers, it was formally about this primal logic, partially because it's about derivation. In access control, you derive things. You derive who is allowed, who is not allowed to do this or that. Typical access control, who will be allowed to do something on this website and so on. Now, in fact, I hinted in the very beginning, it's really about this algebra of infons. So the whole thing is algebraic, but not necessarily group theory. In group theory, I remember now that Yasnikov told me when we just met that in, I forgot his name, there was this group theorist from South Africa. Do you know whom in New York City?
Gilbert Baumschlag? Yes. Well,
so they have a grant from the army or NSA, I don't know, big grant. And so they were building tool to deal with groups.
Yeah, I mean, that was mostly during the 90s, right? Yeah, they were trying to write some computer programs that were implementing.
Right. We discovered that most decision problems, even those which are
undecidable, yes.
Undecidable, in reality, they all kind of trivial. In
some sense, yes, in some sense, no. I mean,
right.
There are, in fact, many problems in group theory that we think, I mean, I don't know whether our definitions completely match with yours, such as like the word problem in chromohyperbolic groups and certain other kind of groups that, at least for us, I mean, are decidable in linear time. For certain other things, they're decidable in quadratic time. Sometimes I forgot, you know, there is this thing, what is it called? There is an algorithm which decides whether one stream is a subword of another, right? You know, which is actually done in linear time, even though the naive algorithm works in quadratic time. What is that algorithm called? Do you remember?
Yes. So you have, say, a long string X and short string Y.
Right. And the naive string works in the quadratic time, but the clever string works in linear time. And I always forget, you know.
So I have an anecdote about this result. It is Knut Pratt more.
Right. Because in group theory we need it because in order to even solve the conjugacy problem in the free group, one actually needs it because if you want to decide whether two cyclically reduced words, and if you want to decide whether one of them is a cyclic permutation of another, one needs this algorithm.
So let me tell you an anecdote about this.
Yes.
Which von Pratt told me that Knut and Pratt are in Stanford, and Morris was in Berkeley. And in both cases, the following happened. So they implemented their implementation of what called Berkeley version of C was it was using this Knut-Morris-Pratt algorithm. And several times the following happened. Something was wrong, and system engineer comes, looks through the code, finds this code, which tries to understand what the code does. Then he understands what the code does, writes, decides code too complicated, write a quick algorithm, which is essentially quadratic, trivial algorithm for this, and the whole system collapses. Nothing works.
Okay.
So n square is extremely dangerous for practical purposes.
I can believe it, yes. All right.
There are many group theoretic problems. I just didn't think in this direction.
I see. Okay. All right. Any other questions to Yuri? Okay. Let's thank Yuri again. Thank you very much.
Okay.
All right. Thank you. So I'll stop the recording now.
Yes. Thank you. Bye.
Stop.